So thanks a lot, first of all, to everyone for the opportunity. I'm really glad that IMA has, has created this group of interest. It's timely, it's important, and I think it's extremely relevant to underline the role of mathematics in this area. So we are, just while we're starting, let's see if it's now, yeah, now it's okay. So I can share the desktop. So you're going to see now my fractal, probably, unfortunately for everyone. And now it's okay. You there? Yeah, good. That worked. So yes, it's extremely important, I think, to underline the foundational role of maths, not only to solve problems, but to pose questions, and to pose questions in a creative and wide-ranging way. So I think that there are different ways to look at the world as a problem to be solved or as a landscape to explore. I belong to the second group. I think the world is a landscape to explore. And even the great challenges like climate change are not problems to be solved. It's a learning process. Otherwise, we solve a little bit and we end up in something even more complicated. I think maths give us the perspective to do this. So today, I'm going to say a few words about tipping point and metastability in the Earth system. So this is a much debated and rapidly evolving field across maths, geosciences, obviously, physics, and more data sciences. And it's receiving a lot of attention in terms of funding through since a long time from the European Union. There's been a growing number of projects delving into this problem, and recently ARIA, the new research agency, has created a large pot of money to address this problem in a quite creative way. And now, very recently, the European Space Agency is also looking into this. So this thing is booming scientifically and in terms of impact, because we have to try to get ready for things that might change qualitatively the world we live in. And this is a big challenge. So an important starting point is, if we look at climate, we have to keep in mind that there is no such a thing really as a reference climate, because the climate is a multi-scale system. So if it's a multi-scale system, it means that it varies on all time scales. It has always varied, it will always vary. Okay? There are, of course, clusters of variability, we will see this at the end, which have a great importance for the development of ecosystems, of different habitats, and so on, of our species. On the other side, this does not contradict the fact that we are observing a distinct climate change on certain time scales, and that we can attribute this to human agents, among the others. And actually, the way to address this, it's actually quite sophisticated from a mathematical viewpoint, because you have to assign the relevance of one path in a stochastic system. One path in a stochastic system, in some sense, it's irrelevant mathematically, but we live in this path. We don't have a multiverse. So statistical mechanics, which I like ensembles, so here we need to lift the problem to an individual path. This is very non-trivial, but I'm not going to talk about this today. As I said, tipping points. So this is there is a large variety of maps of this sort. So tipping points or tipping elements are subcomponents of the climate system that can undergo rapid irreversible transition. There is a lot of debate on the clear definition of tipping points. I will propose one as a result of the ongoing climate change. Of course, rapid transition in subcomponents of the system have always happened and will always appear. So the one you see now in the map are those that have been deemed in the last, let's say, 15, 20 years of research to be most susceptible in sort of, reasonable time scales. So the one that directly impacts, of course, the Western Europe is the Atlantic, the shutdown of the Atlantic overturning circulation, and the change in the Arctic sea ice and the ice sheets in Greenland. Of course, there is these elements have a huge regional impact, but they also can have a global impact if we consider then longer time scales. So again, the problem has to be cast precisely in terms of what we are interested in. There is not a silver bullet. We put a question, we get an answer. Things are a bit delicate here. So now, what is again, the sort of qualitative way to look at this? On the top left, I'm reporting an important study, it's already 20 years old. What at the time was quite innovative, to do an intercomparison study of different climate models that showed that indeed, if you look at the Atlantic meridional overturning circulation and you impose an extra freshwater flux in the North Atlantic, different models did see a decrease and then a collapse of the circulation and the clear hysteresis behavior. That is, when you come back, you don't immediately recover the initial circulation. So this was a very important study. Replicating those results in a comprehensive climate model has proved more difficult than it was expected 20 years ago. So this is a difficult problem, but it is also a problem with huge relevance. How do we see, let's say qualitatively, this is a classical way to explain this sort of transition. Assume the world is a one-dimensional potential. With some noise, I perturb a parameter and I can lose stability in one minimum. So this is a very good, it's a very easy way to represent it, but I believe this is not a good way to describe what the system does, because the system lives in a very high-dimensional world. Nonetheless, there is a mathematical framework to cast things in something of this sort. Instead of talking about potential, energy potential, we talk about quasi-potential, and we have to live to a higher level of abstraction. But something like that works. The nature of noise is another very important. What is noise? And the nature of noise is a very non-trivial question. Now, another way to see these tipping points is the following. I have a system, so the right to see the image, more or less, this is taken from a series of publications of Tim Lenton and collaborators who have played a huge role in bringing this to the public attention, and they deserve a lot of credit for that. Now, I think we need to go a bit deeper in some mathematical aspects, but another way to see the tipping point is that you have a forcing, and in some parametric range, you have a smooth response to a forcing, and in other parametric range, the response is enhanced, and then we have a breaking point. So the tipping point is realized, in other terms, in let's say system theory terms, when the negative feedbacks are overcome by the positive feedbacks. That's a way to see it. So the system breaks down. So this is the angle of sensitivity and the angle of response theory in statistical mechanics. Okay, now going into the data world, one can prove actually with the angle of response theory. That's a work some of us have been doing with a lot of attention. And here there is John Moroni, a collaborator of mine in Leicester. We are also working on these things. The occurrence of this transition is associated with the emergence of specific patterns which dominate near the tipping point. And how to extract this pattern from data is a challenge that one can try to address using deep learning technique that extract. So the math tells us that this pattern exists. Data analysis can allow us to extract these patterns. Now, let's go to why people study the AMOC. Why there is all this interest by, the global north, in studying the AMOC. Well, this image, I think, tells you a lot. So this is the regional impact of a collapse of the AMOC. Have been studied since many years. This is a relatively recent study, but what you see is that if you shut down the AMOC, you create a cold blob in some of the richest parts of the world. So that's why, and highly populated part of the world. That's why people care, obviously. Now, what we see is that indeed, in some parts of, especially the British Isles and Scandinavia and Central Northern Europe, this leads to a fundamental change in the climate conditions. So basically, the UK in this scenario becomes a barren land. Okay, nothing basically grows. So this is how it is. So we have a decrease of temperature, massive decrease of temperature, huge decrease of humidity, and the agricultural productivity, this has been studied in many studies, will decrease like substantially. So so this is the real sort of problem for. So we understand that in the past, events of this sort will extinguish basically a population, okay, or make people migrate in mass. That's how things. Now we live in a technological society. We can deal with it better. But anyway, this is massive, and there's been a lot of attention is growing. There are a lot of initiatives. There was recently a workshop we had in Leicester. Next year, there's going to be a month-long program at the Isaac Newton Institute on exactly on this topic. Please get in touch if you're interested. We are still sending out the invitation. Now, where does the story of tipping points come from? What is the tipping point? The tipping point is the transition between and the existence of bistability of the Earth system between warm and snowball Earth. So now we go back to the late 60s, basically the beginning of climate science in some sense, and the two extremely prominent scientists, Budico and Sellers, were studying using a reaction diffusion model describing the energy balance of the planet on a one-dimensional, so what today would be a simple toy model, and they discovered that indeed, these models could have two solutions, one corresponding approximately to the warm state and one corresponding to a state of global glaciation. Of course, everyone thought this was just mathematical curiosity. Nicely enough, they were not studying this because they had in mind the paleoclimate. They were studying the potential impacts of global nuclear warfare. What happens if we shut down the sun because we have too much soot in the atmosphere? So this is sounds eerily contemporary, okay? So this is a very serious matter because, and what they understood is that not only if you switch off the sun for a while, not only obviously the Earth becomes colder, but when the sun comes back, you might have crossed a tipping point. And indeed, many years later, it was discovered these events did occur in the Earth's history, and they've been essential for the evolution of life on our planet. So we had a lot of failed attempts to multicellular life, maybe, and so multicellular life emerged about 500, 600 million years ago, well after the final transition between snowball and warm, because there is no multicellular life in a planet with minus 50 degrees at surface. So this is the simple model, it's very similar to the simple model that these guys were studied, and the key effect is the presence of the so-called ice albedo feedback, a positive feedback. Warmer temperatures tend to have fluid water has high absorptivity, cold temperatures tend to have snow and ice, which reflect a lot of sun. So in a nutshell, this is the key element, the key instability associated with the existence of bistability. And you get a phase diagram of this sort that we can study, of course, accurately. We get a warm state, a snowball state, and the tipping point, the one associated with parametric modulation, is in a dark red on the left. So meaning that if I switch off the sun, so I move the solar constant to lower values, I'm not talking zero, of course we reduce it, I can fall in the snowball and I don't come back very easily. So this is structured, this is fundamentally correct. So even if you take a very complex climate model, it gives you something very similar to this. And then of course, there are many other transitions there, but this is the key one. And now it's 12 years ago, my former PhD student of mine, Robert Boschi, from a British guy, by the way, an extended series of RAM and also studied the impact of CO2 modulations. Now, the mathematical question is, what lies between this warm state and the snowball state? So is there something in between? Of course, in a simple model, we just find a fixed point, but what happens in high dimension? So what happens is that if you take some mathematical results proposed in the 80s by Ott, Krebogy, and York, you discover that if you take a contractive system with multi-stability, you have two basins of attraction. I'm taking the simplest case. There is a basin boundary, and there is in the basin boundary, so what separates the two basins of attraction, there is a special set, which they call edge state, which acts as a relative attractor. So this object, the pi1 here, attracts the initial condition on the basin boundary, so it's an attractor except for one unstable dimension. So it's an unlucky attractor. It's not a climate state because it's unstable, but it defines the existence of two states and not just one. It's a sort of a dynamical separatrix. Now, it's clearly to understand the global properties, we need to capture this object here. So it is possible to capture it. And now I'll try to tell you why this object is important. So one, there is we were having a discussion before the beginning of this event, saying, you know, why is mathematics useful at all in the world of abundance of data and data analysis technique, almost prodigious. So I think this is a good example. So if I analyze a lot of data, what I will see is the existence of the attractors. I will see the attractors, I will see the transient going to the attractors, but I will never see the object that you never see. So this pi1, it's a ghost. Doesn't exist in your data, but it's there. Because to see it, you will need to populate a set with measured 0 that you never see. So why is math useful? Because it tells me that this object exists. And data will not easily find it, probably will not find it. So it's useless in some sense, but it determines the property. So I think that's why it's very motivating for me. So now, with my friend and colleague, Tamás Bodai, who is now in Hungarian, now is in Hungary, we managed to construct this edge state that we call the melancholia state. In the case, it's chaotic, or a simple, relatively simple climate model. Relatively simple, I mean, about 10 to the 4 degrees of freedom. So it's not so simple. So what you obtain is that you have the warm state and the snowball state, which more or less corresponds to what we know. And then there is this intermediate state, which is strange. It's just strange. It's a strange state that lives on a sort of on a mountain pass, basically, technically. But it's very real, and indeed, it pushes away trajectory initialized near it. So it's this sort of ghost, and this word ghost will become more technical in a moment. Now, mathematically, there is now, again, why is math useful? So now we look, we started to think, okay, now there is this basin boundary. Okay, so then if I have to separate, cut into an n-dimensional set, the separation has to be at least n-1 dimensional. And my intuition is that it must be a manifold. But actually, you can prove that in many cases, especially if it's chaotic, it's not a manifold, but is a fuzzy set. So what it means is that you have these two attractors, then there is an intermediate region, a gray zone, with co-dimension, which can be small, and in many cases is very small. So it's like a fractal set in between that separates the two. What does it mean? Is that once you get close to this region, you could jump between the two end states without any control. So the resilience of your system goes to 0. So there is a danger zone where you flip a coin and you go where you don't want to go. So this to tell us that we might underestimate the risk due to keeping points, because in phase space, there are these fuzzy regions that act as a wormhole and mathematically, that's exactly what will happen, from one state to the other. So this is, I think, quite interesting. Now, going back to this Atlantic meridional overturning circulation, I want to show a couple of things that have been obtained by my student, former student, now is in Utrecht, Rijk Börner. So Rijk is passionate, is already a great scientist, is going to become even greater scientist. And you wanted to tackle the problem of AMOC, of the Atlantic meridian, of the multi-stability of the AMOC, using this, what I would call a global viewpoint. So what it did is it took a climate model, which has a sustained AMOC and in the parametric regime, a coexisting off state. So it's a model which more or less works. And it tried to find the edge state in between. So can we do this exercise? So now we are trying to find a non-existent oceanic state that makes sure that these two competing states exist. And can we learn something from it? So this is you know, most test. I mean, it did an amazing job. So what we have is this. So we have, this is on the top, you see a time series of AMOC intensity in the strong state, so today's state, and this is the collapse state, the state we don't want. Okay, now, how do you find this edge state? So the methodology was developed in the early 2000s by a group of people, including the late Bruno Eckert, who was professor in physics in Marburg, and is the person who taught me to do this, to follow the strategy. Unfortunately, he passed away a few years back. And now what you do basically is that you want to find, so you have the orange and the blue, and you want to find the green, the unstable state. Remember, this state will push you away. So the methodology is through what is called edge tracking. So it's a bisecting method by which you basically try to find two initial conditions on the two sides of the basin boundary, and then you push them forward in time, and then you do another bisection to find the two nearby initial conditions on the opposite side, and you go on like this, and in the limit you get a trajectory on the basin boundary. So this is a generic methodology which is not hard to implement in a simple model, but in a very high-dimensional model where there are lots of challenges. And these had never been attempted before Reich did. And so basically you have to make sure you stay in this mountain pass. But remember, in this case, the state is not a point, it's a turbulent ocean circulation and climate dynamic state. So you want to find an unstable climate state. It's very hard, but it works. So basically what you do is that you bisect, you see that you abandon the orange and blue trajectory sequentially until you hope to find a trajectory that lives in the boundary. And actually, after a lot of sweat and blood, you get it there, because you get a consistent state. So in some trajectory, you have the off state, you get the on state, and you get this edge state. So this edge state exists, it's there. You can make it better, but it does exist. And it's quite miraculous, because now I put the hat of the physicist, which is the person I'm originally in, and you find that this edge state has a very good energy balance. So it's not out of energy, it's physically consistent. It's just dynamically unstable. But physically, it has a zero top of the atmosphere energy balance, it has a nice energy transport. So it fits, you know, the sort of consistency properties, but it's unstable, too bad. So it's a possible state, but unfortunately unstable. And now what you see is the tipping. Now I tell you what is the tipping point mathematically. So we see the possibles instead of just what we see. So 285 ppm is the pre-industrial, and 360 is the reference, and 460 is the future. Of course, don't take these numbers too seriously, but let's see what happens with the parametric modulation. So you see the on state, the off state, and the edge. And as you clearly see, as we increase the CO2 concentration, this edge state encroaches the on state. So we touch that there is a boundary crisis, the edge state touches the on state loses stability, so they shake hands and disappear in phase space. What is left, and this is very fascinating, is you see that sort of double cluster of variability. This is what mathematically is called a ghost attractor. So what we experience is that when you get to 460, we have what is called a long-term, long transients. So the system lives in this state for a very long time or for a very short time, you don't know, until it eventually collapses into the off state. So the off state is the only climate state, but you could live off the transient state for a very long time or very short time. You don't know, depends on the initial condition. You can define a random, some probability there. So now, as an example, it could well be that we are in that state. You just don't know because you don't have many other realization of the world. It's quite disconcerting. So we might just live in a long transit. Of course, we always live in a long transit, right? And at the end, the sun is going to burn up. Whatever. So anyway, this is, I think, it's a quite fascinating angle. So we see now what is the collapse of the EMO. It's not just magic. Something magic is the edge state touching and taking over the on state. And that's it. Nicely enough, the edge state, you see the green line, has these very long extended centennial fluctuations. And we can see that these fluctuations are related to the transport of salt and ice in and out of the Arctic. So you can find a nice oceanographic correspondence to this. These are not like strange things. Now, you can repeat, the oceanographer, your best oceanographer friend will say, yes, but this is not a good ocean model. This stops the conversation, right? So it's like, so, and this way. But you can take a more advanced model of the ocean, and you can find something even nastier, which is good. So this is mostly due to Johannes Lohmann, another very brilliant guy who just got the early career award by SIAM group of mathematics of planet Earth. He's assistant professor in Copenhagen and involved in this work, where he did one of the most painstaking exercise ever. He took an ocean model and ran it for something like 8.5 million years. How? He started to play. You see this, the top right, you see this is similar to the bifurcation I showed you before. That was very smooth and clear. So what he did is, instead of just believing that things are smooth, he started to go back and forth a little bit, just poking the system. A bit, I increase the fresh water, then I reduce it. And then I increase it again, and then I reduce it. He was trying to find a hole in the phase space. And incredibly, he succeeded in creating an object like this. So suddenly, this nice bifurcation diagram breaks down in a multi-scale sense in many, many other bifurcations that we could find. So basically, if you go back and forth where you have C, E, F, G, you don't fall back into the initial branch. There is another branch hidden somewhere. So I was very surprised. We talked about this, and then we discovered that there are different convective patterns. So somehow it means that the dynamical landscape is not just on and off state. There is a multiplicity on smaller scale of state. So we have this beautiful image, I believe, that the stability is not just, two-party system, fortunately. There is more. There is more variety. Now, locally, you might be so in other terms, there is a hierarchy of tipping points. And these tipping points will have different role in spatial and temporal terms, okay? But they are there. They are there in the system. We don't see them, but they are there. So somehow, instead of having, a bifurcation diagram like the one on the bottom left, which is our comfortable one, because it tells us that until we don't get to the green star, we are safe. Our safety could disappear much earlier because there are other little things, but other little things might impact. So if you shift the convective pattern by 1,000 kilometers, the global ocean circulation doesn't care, but the British Islands do. Very much, okay? So, concluding, the same game exists also for this ocean circulation. So also on these much more sophisticated, higher scale, higher resolution more turbulent state, you can still find this complex object in between. So the message I want to give is that first, mathematics can help us go deeper in this, addressing this problem, finding new questions, not only answering the questions we have, and that if we want to have a real assessment of the risks associated with tipping, we need the global viewpoint. The side story of this is that early warning indicators, which are very important, tell us that we are losing stability where we are now, but are not telling us where we're gonna end up. Okay, and I leave with this, some fluctuations about the social, our geopolitical and social status. We know there are instabilities. We don't know what is the outcome of these instabilities, and we should not be too confident on our ability to control. Okay, thank you. I stop here.